Of this session is Professor Marta Sansolé from Barcelona. She will speak on large deviation principle for stochastic wave equations.
Yeah, thank you very much. So I would like to thank the organizers of this semester for the invitation to the workshop and for the long stay at the Institute. And so I will speak on large deviations for a particular equation, which is a stochastic wave equation in dimension 3. So this is the equation I will consider to start with. So this should be in red. I don't know if you can see it properly. So at the moment, forget about the epsilon. And you have a usual wave equation with some non-linear free terms and perturbed by a noise. And I will be more precise later on what kind of noise I am considering. So this is on our time is a finite interval. Epsilon will be a parameter, a perturbation, and the initial conditions are, as usual, I'm sorry. Initial conditions are, as usual, for the second order partial differential equation. And space will belong to R3, okay? So there has been already some results on, so in this conference, some results on large deviations for the stochastic wave equation, mainly in the talk by Professor Sapchik. But my setting is different for several reasons. So one of the reasons is that, well, noise here will be Gaussian. I will tell you precisely later on what kind of noise. So I am not dealing with Levy processes, so to say. And another strong difference is that here I will be interested in random field solutions to this equation. So that means that at the end I will have a solution which depends on both parameters t and x. And then, well, the main result on this sort of equations is has been published in this long paper jointly with my colleague Robert Dalin, who just appeared last year. It's a memoir of the AMS, where we were able to prove, and I will be also more precise in later on, that giving a suitable formulation to the equation and of course on appropriate assumptions, then we have been able to prove that a random field solution to this equation exists, and the sample paths are Hölder continuous jointly in time and in space for some also precise degree of Hölderianity. So then with this setting, the objective of this talk is to establish a large deviation principle in the Hölder norm. So this will be a quite sharp result. And well, this is ongoing joint work with a student of mine, Victor Ortiz. Okay. So then the outline of the talk is that one. So it will consist of 3 parts. So in the first part, I will give some very elementary presentation on the weak convergence approach to large deviations. So it has been mentioned very quickly in the last talk yesterday by Tu Sheng. It has been also mentioned in the morning by Professor Sapchik, and now Annie has also given a few elements of the method. But since I see so many young people in the audience, and I think that many of them maybe, and also, yeah, so young and not that young people that don't know either about the deviations or about this approach, I will be quite explicit on it and a sort of lecture. Okay, so this will be the first part. Then in the second part, I will be the necessary elements or article with Robert Dalang on the stochastic wave equation in dimension 3. And then the third part of the talk and the last one will consist of the stating the result on large deviations and give a sketch of the proof. So first thing, you have already seen that many times, so I will pass quite quickly on this first slide. So this is the formulation, the classical formulation of a large deviation principle. So the setting is you have a Polish space, and you consider you consider a function I, which is lower semi-continuous, and such that the level sets are compact. So these are good rate functions, but I will just quote them as rate functions. Okay. And then, so large deviations is a quantitative result on how a family of probability measures degenerate to a measure concentrated on a point. Okay, so if this degeneration takes place so in a large deviation style, then we say that the large deviation principle holds, and this degeneration is given in terms of the rate function. And more precisely, what holds is that for each closed subset, you have this upper bound here, and for each open set, you have this lower bound here. So the degeneration takes place in an exponential fast way. Okay, so this is what a large deviation principle tells you. Okay, so there is also the so-called Laplace principle, which can be stated in parallel with the two conditions before. So we'll say that a family of random variables, so these random variables take values on this Polish space E. So this satisfies the Laplace principle upper bound if with the rate function I, if for any bounded continuous function H, this quantity here, which is epsilon times the log of a Laplace transform at point 1, say, the lim sup of this is less or equal, so can be described as less or equal than this quantity here. Okay, and something similar for the Laplace principle lower bound. So then instead of less or equal, you have greater or equal here. Okay, and there is a well-known result saying that a large deviation principle in the form I have stated in the previous slide is equivalent to the Laplace principle, in the sense that upper bound is equivalent to this upper bound here, and lower bound is equivalent to this lower bound here. Okay, so then as Annie mentioned in her lecture, so there are some standard methods, or maybe not so standard, but they are methods in order to prove large deviation principles. And one idea is, okay, let's try first families which are easy to handle, so to say. For instance, Brownian motion perturbed by an epsilon. Okay, so then assume that we are able to prove a large deviation principle for such simple processes. And for example, in the case of Brownian motion, this is the Schilder theorem. Okay, so once you have a large deviation principle for some family, then you can try to transfer this principle to much more complicated families of random variables, which are obtained by transformation of some functional G, which may be very complicated, of this basic family B epsilon. Okay, so then this transfer is very easy, so it's trivial in the case where the functional is continuous. But this covers very few interesting examples. For example, if you consider a stochastic Ito equation in dimension greater than 1, so this is not the solution is not a continuous functional of the noise. So even in this simple example, you don't have continuity. Okay. So there have been many results on for transferring the large deviation principle, and this is all work by Azencott, Dos-Priore, Wenzel-Frelin, and so on. So there are many people, but they are always in the first formulation of the large deviation principle, so the first slide, okay? And roughly speaking, this transfer is done by an exponential control of the lack of continuity. So of course, this doesn't tell you very much because it's not an explicit statement, but it's an idea, okay? So now, if instead of taking, so to say, the classical formulation of large deviations, we consider the large deviation principle in terms of formulated in terms of the Laplace principle, then this transfer procedure is done, well, apparently, I would say, in a different way. Maybe it's not very different, but it's well, it's a bit different. And this is what essentially Ellis and Dupuy, and then later on Boudiraj and Dupuy, and Boudiraj, Dupuy, and Maroulas, and Bouet and Dupuy have set up in a series of papers. So here the key step is what is called a variational representation of this basic process. Okay, so let's consider a Gaussian process. I don't think that, well, I don't know if such a variational representation may be extended to non-Gaussian processes, maybe with other procedures. I am not sure of that. So what is a variational representation of a Gaussian process? So let's take an example. Let's do that in a particular example, and I have chosen this example because this will be essential in the case I will consider later of the wave equation. Okay. So the example I am considering is that of a sequence of independent Brownian motions defined on 0t. That means this is a random variable which takes place in the space of continuous functions defined on 0t and taking values on the space of sequences, so there are sequences, okay? And then a fixed, so let G denote a bounded and measurable function which is defined on such a space and which is real valued. And we'll denote by PL2 the set of predictable processes which are sequences, actually, okay, which belongs to this space. So then a variational representation for this process is an equality like that. Okay, so it's an expression for minus the log of the expectation of the exponential of minus GB in terms of a variational formula. Okay, so this is given by the infimum over all predictable processes in that set of the expectation of this random variable here. Okay, so this is deterministic shift, and this is the noise. So for finite, in the finite dimensional case, this result has been presented, stated in this article by Bouet and Dupuy. And then for other sort of noises, well, for a Wiener process, an H-Wiener process with a finite trace, it's stated here, and this result is stated here. Okay, so this is a basic result, and then now the question is. Well, maybe I will say some ingredients on the proof of the result. So this is a very simple result, actually. It's not very complicated. And the idea is, so the proof of this result relies upon one abstract equality, which is that one, plus Girshanov theorem. Okay, and this equality here, which is well, actually formulated in a completely abstract framework. So you have a measurable space, a bounded, so random variable, if you wish, and then you consider the set of probability measures on this measurable space. So I recall you the definition of the relative entropy of gamma with respect to p, where gamma and p are probability measures, which are absolutely continuous. And then it's not very difficult to prove that you have such a formula for the minus log of the expectation of this random variable. Okay? And then on the basis of that, using Birsanov theorem, you get of course you have to work a little bit, but you get this sort of variational representations for processes. So this is a nice result. Okay. So now, once we have this variational representation, in what consists the transfer? So what are the ingredients we need for transferring a large deviation principle? Okay, and the key word is weak regularity. So let me give also the ingredients for that. First, a notation, which yeah, more or less appeared also in Annie's talk. So I will denote by Sn of L2 the set of functions, so these are deterministic functions with bounded norm by n, and Pn of L2 will be the set of predictable processes which are bounded. So this is the definition. And you have to keep in mind that on this set I will always consider the weak topology. Okay? So this is the weak topology. So now I will consider a function, a functional G, defined on this space, taking values on E. Okay, so this will be the function which will provide me with the family of random variables I would like to transfer the large deviation principle, and we assume that there exists also another measurable function which I call G0, such that two properties are satisfied. So the first one is that the set built up in that way, so is the image of G0 by elements of this set, it's a compact subset of E. Okay, so this is the first condition. And then the second condition is stability, which says the following. So assume now that we consider a family of elements of here, so predictable and bounded processes, which converges almost surely in distribution to some element of the same set as Sn L2 valued random vectors. Okay, so this convergence in distribution in the weak topology. Okay, so then the assumption is that the limit as epsilon tends to 0 of G, when applied to the shifted infinite dimensional Brownian motion perturbed by the factor square root of epsilon by a shift of this set, then these converge also in distribution as E-valued random variables to G0 of U. Okay, so this is the stability.
What was E, capital E?
Capital E is the set, is the image of here. Okay, this is Polish space.
Of sequences or?
No, it can be arbitrary. It's
Oh,
Polish.
that's the basic.
Yeah, this is the basic. Yeah. Okay. So this is the hypothesis. So then the result proof in the paper I mentioned, so VDM by Badurija, Dupuy, and Marolas in 08 says the following. So assume that, so let fix x epsilon to be the image by G of square root of epsilon B. Okay. So and then we define the candidate to be the rate function. So I of f is the infimum of the energy. Okay, so these are elements of L2, the deterministic elements, so 1 over 2, the square root of L2 norm of U for all U's, such that through the functional G0, they go to F. Okay? So here, the controls are U, if you wish. So then, assuming that the assumptions H1, so the compactness and the stability hold, then it turns out that x epsilon satisfies the Laplace principle with rate function I, which I recall for you that means that this limit is equal to this quantity. Okay? So this is the abstract result. So this is not a very surprising result, and I will show you in a very sketchy form why this is true. Okay? So this follows from the variational representation, and this follows this, well, quite easily because of the following. So in the variational representation gave you a representation for the log of the expectation of GB, of minus GB, okay, or the exponential of minus GB. So here you have the choice, many choices, and you will choose as G of B exactly, so this is the candidate, okay? So then the variational representation, so just you copy the variational representation and you get an equality like that, okay? And then the idea, of course you have also to work, but the idea is that the stability, the limiting hypothesis that I call H2, H1 is typically a condition to prove that I is a good rate function, okay? So then the stability tells you that working on this quantity here, you will get the HF. And HF is one of the ingredients here, okay, for the Laplace, for the Laplace principle. And working on this, you will get the rate function, which was the other ingredient, okay? So in fact, I mean, what could be difficult, and this is what we have seen in the examples that Annie has presented, is to check the hypothesis, especially the second assumption. But once you have these assumptions, so this sort of transfer is pretty easy. Okay. So this was the tutorial, and now I will start with a new topic. So now I will tell you something about the stochastic wave equation in dimension 3, which we are going to consider. So this is the same as in my first slide, except that, well, here there is no perturbation because I am starting the topic, okay? So, what is important here is to give an accurate description of the noise. So the noise we are considering are Gaussian processes. So I will consider this is the formal derivative of a process which is indexed by smooth functions. So C infinity, compact support, which are Gaussian, zero mean, and then the covariance is given by this formula here. The star means the convolution operator. And gamma is a measure on R3 which should be nice enough in order to assure that this is a covariance function. For example, it should be non-negative and non-negative definite as a distribution and tempered measure, okay? So because of this form here, you see that your noise is white in time and correlated in a space, and the correlation is given by the measure gamma. But this is stationary. It's a stationary correlation because of the specific form of the covariance. So this is the noise we are going to consider. So now, what are the assumptions we have been considered in the paper with Dalang? And these are assumptions H will be fixed for the rest of the talk. So the assumptions on the coefficients are not so very general. Sigma and B are Lipschitz continuous, okay? And then concerning the correlation of the noise, so the covariance, of the noise, we have considered the case where gamma is absolutely continuous with respect to the Lebesgue measure, and where the density has two components, one which is very regular, this is the contribution of phi, and another one which is singular at zero, this is a Riesz kernel of order beta. Beta should be, because of integrability requirements, less than 2, and concerning phi, it should be of class C1 with a gradient which is Hölder continuous and bounded, and well, the Hölder degree is called delta. Okay, so this is concerning the noise, the irregularity of the noise. And then concerning the initial conditions, we want to deal with non-null initial conditions, and these are the hypotheses. Okay, so it's of class C2, D0, with a gradient and b0 square, which this was the derivative and this was the other one, is Hilbert continuous with degrees gamma 1 and gamma 2 respectively. So there are here 4 parameters, the beta, the delta, the gamma 1 and gamma 2, which will be important in the statement of our results. And so just for those who are familiar with this sort of noises, the hypothesis 2 implies that this quantity here is finite, where mu is the spectral measure of gamma, that means the inverse of the Fourier transform, and script f stands for the Fourier transform. Okay, so under this is an integrability assumption which plays a very important role in the construction of the stochastic integrals and so on. Okay.
Capital G, what was capital G?
Ah, yeah. So capital G, yeah. Sorry. I will give you now the definition of capital G. So we have considered the mild formulation of the equation, and here it is. So we say that U is a solution to the wave equation if U solves an equation like that. So let me explain a little bit that. So W of Tx is the contribution of the initial conditions. Okay. So this is what you will get if you consider a deterministic wave equation which is homogeneous. Okay. So sigma equal to 0 and b equal to 0. And then you have these two extra terms where G is the fundamental solution to the wave equation. Okay? And it's well known that in dimension 3, this fundamental solution is given by, so modulus this factor, this normalizing factor, is given by the uniform surface measure on a sphere of centered at 0, a radius t. Okay, and this is one of the so this explains why we are interested in dimension d equal to 3. Okay, because this is, well, this is somehow a difficult case, because well, this is a measure, while in dimension lower than 3, the fundamental solution is a function, and then computations are easier. And in dimension greater than, strictly greater than 3, it's a true distribution, and then things are quite difficult, even though there are results by Péchat and also by Conus and Dalang on equations on higher dimensions. But I think, well, d equal to 3 is somehow a threshold. Okay, so here this is the usual term you will have also in the deterministic case, where when you add a non-homogeneous term called v, so this is the convolution, and this is the stochastic integral, which gives you a rigorous meaning to the equation. And I will explain a little bit what sort of a stochastic integral we are considering here. Okay? So this is also a convolution. This is a stochastic convolution, but I should give an explanation of that term. Okay? So for technical reasons, but I should mention that, even if you will not see really that, because I won't give the proofs, we have considered this equation localized. And the localization, because we were interested in Hilbert continuity, so we have proof of Hilbert continuity in any domain, okay, in any bounded domain. And so the right localization is performed via sets which are related to the light cone, which is, well, completely natural because of the framework. Okay, so this is one ingredient we have used in the formulation. Okay, and then the other ingredient I would like to report on is on the stochastic integral we have considered. So the stochastic integral we have considered is one which appears in a paper by Dalang and Müller. I think that is in 2003, if I remember well, where so they have defined a stochastic integral. So here I am dealing with the fundamental solution of the wave equation, but in this article they deal with more general distributions satisfying some assumptions, okay? And they are satisfied by the fundamental solution of the wave equation. So I won't be very general here, so just I will stay at my example of the wave equation. So the objective is to define a stochastic integral where the integral looks like that. So here you have the fundamental solution of your equation, and here you have a process. And you can do that if z is adapted, mean square continuous, and L2 valued. Okay? And the stochastic integral is actually gives rise to an L2 valued random variable. And the construction is such that it satisfies an isometry, which well, may look a bit difficult, but it is not. So here you have the Fourier transform of z, okay, the square, and here you have an integral which already has appeared more or less in the same form before, okay. So this remember that was the spectral measure of the covariance, okay. So you see that, well, if z is in L2, and you can, for example, take the supremum over xi of this quantity, and this is finite, then a condition, an L2 condition, an integrability condition in L2, plus this condition on finiteness of the supremum of such a quantity will give you that this is finite. And this is essentially what happens when you are dealing with the wave equation. Okay. So, so this is
the last thing that you said, and you mentioned before that DeLong manages to go beyond the wave equation.
Sorry?
You mentioned before that DeLong goes beyond the wave equation.
Well, the formulation in the article of DeLong and Mueller is, so let's consider a function which take values on the set of distributions with rapid decrease, which satisfies that, and that, okay?
My question was, do they use this uniform boundedness in the parameter of psi? They still use that?
Yeah.
Okay. All right.
Okay, so this is a very brief summary of the article in the memoirs. So assume the hypothesis H I have mentioned before, and then the result is that there exists a random field solution to the SPDE, to the stochastic wave equation, with Hölder continuous sample paths. And so this conclusion here is a consequence of estimates of this type. So in fact, what happens is that for an arbitrary Q, an arbitrary alpha on this interval, so you see this interval is determined by conditions on the initial conditions, gamma 1 and gamma 2 of the equation, and conditions of the noise. So beta was the order of the risk kernel, and delta was the Hölderianity degree associated with the regular part, okay? So what you have is that LQ increments of the solution at two different points, Tx and T bar y, are upper bounded in mean, are upper bounded by this sort of quantities, okay? So as I said, this is really a very brief summary because this is a long article, but more or less the steps of the proof consist in the following. So I told you that we consider the localized equation. So first we prove existence and uniqueness in the space, so in the space of random variables taking values on this space and which are in LQ. Okay, so first there is a sort of a functional approach, right? Because the stochastic integral was a function valued random variable. So then the most difficult part was to prove that in fact the solution as a function valued solution lives in a fractional Sobolev space. So this W alpha Q is the fractional Sobolev space of order of fractional differentiation alpha and order of integration Q, okay? And then once we got this result, which was the most difficult part, then we can use Sobolev embeddings and therefore conclude that for each t, actually uniformly in t, the solution has Hilbert continuous sample paths in X. Okay? And then this allowed us to fix in the solution an X and to see what is the behavior on t. And this part was much easier in comparison with that one. So in fact, these sort of ideas are very present in other works on SPDEs. And well, for example, maybe one reference is all the work of Krylov and co-authors. Okay? So now, of course, going back to the large deviation, we would like to use the results that are already in the literature. And for this, we are going to reformulate our noise, okay? And this will be done in a very standard way. So this was the noise we were considering. I recall just the definition here. And now we are going to attach to this covariance Hilbert space, which will be the completion of the set of test functions with the inner product given by this formula. Okay. And then with this, you can define in a usual way cylindrical Wiener process on H. Okay? This is done by setting BTH equal to this integral, where this integral can be understood in the Walsh sense, if you wish, or in the Dalang sense, or in whatever sense, because now H is in the space, in this Hilbert space, it's deterministic. Okay? And of course, once you have the cylindrical Wiener process on H, then you can also see it as a sequence of independent standard Wiener process. So this is completely standard. Okay. So then it's also well known, and there are a lot of references for that, and mainly the book by the Praton Sapchik, that predictable processes can be integrated against cylindrical Wiener process. And the stochastic integral can be defined as a stochastic integral with respect to this infinite dimensional Wiener process. But now the point is, what is the relation between this formulation, which will be suitable in the sequel to study the large deviations, and the formulation of the stochastic integral in terms of Dalang and Müller, for which we have the Helder continuity results. And there is a very nice article which has been just been finished now by Dalang and Kerr, where this is really like well, it's I really recommend it, because they give a description of well, most of the stochastic integrals which are on the market in the infinite dimensional case, and then they give relations between them. Okay, so this is, I think, a good reference to help different communities to talk to each other with the same language. Okay, so and in one of the results of this paper, they prove that in fact the Dalang-Müller integral we are using in our article coincides with this integral in this sense. So that means that you can, so this process here, under the hypothesis of Dalang and Müller, actually belong to this space and therefore can be integrated, and the integral coincides in this space. Okay? So these are good news, because we can use alternatively both formulations. So now I am entering to the third part of the talk. So the large deviation principle. And now from now on, I will assume that the initial condition is 0, okay? In fact, one of the reasons why we used the Dalang and Müller formulation was to include the case where W is not 0, okay? But now for simplicity, I will assume that the initial conditions are 0, and therefore their contribution are null as well. So let's consider the mild formulation, but now with this stochastic integral, infinite-dimensional stochastic integral, okay, or if you wish, or setting. And together with that, we'll consider a deterministic equation, evolution equation, which mimics that one. This is what is called the skeleton, where here H is H is an element of the space L2 of 0t taking values on script H. Remember that the script H was the Hilbert space associated with the covariance of the noise, right? Okay, so then, of course, each element from here can be also identified with a sequence of elements in L2 by the same way that we did with the noise. Okay, and then you consider this evolution equation. So another issue, but this is just technical, is that in all the setting I have said that we are dealing with a Polish space. And this Polish space, roughly speaking, in our case, will be the space of alpha Hilbert continuous functions, which is not separable. But there is an easy way to, to move from this space to another one, which is a little bit bigger, okay, and which is separable. So let's skip that technicality. So maybe I should say that in the rest of the talk, the reference space will be this space of alpha Hilbert continuous functions, but not exactly that space, but a little bigger one, which is separable. Okay, and alpha will be always on the interval where we know that the solution is alpha Hilbert continuous. Okay, so this is the reference space. So now, what is the large deviation principle? So this is the statement. So we assume all the assumptions that give us a solution to the wave equation living on the space of alpha Hilbert continuous functions. Okay, and we have perturbed our equation. You remember? We have perturbed our equation by this parameter epsilon. Okay, and then the result is that this family satisfies a large deviation principle on the space of alpha Hilbert continuous function jointly in T and X with a rate function which is given by this formula here, okay, which is, well, completely, this is the result what you expect. It's not surprising at all. So, and to prove this result, I will use the weak convergence approach, okay? So now I will change a little bit the notation. Again, I will denote by PH the set of predictable processes belonging to this space, and then I will put a superindex here, n is fixed, to denote that I am considering elements of the Hilbert space HT. HT was L2 of 0t taking values on script H, which are bounded. So this was before that one, but can be identified with that also. And PHN are the set of predictable processes which are bounded, so such that almost surely V is in this space. Okay? And now the two functionals which play here again an important role are G, which is defined on the set of sequences of continuous functions where the Brownian motion, the infinite-dimensional Brownian motion lives, taking values on this Hilbert continuous functions space, and the definition of G will be that one. So it sends the perturbed Brownian motion to the solution to the perturbed equation. Okay? And then G0 is a way to write the solution to the skeleton. Okay? So, remember that we have to prove this condition of weak regularity. Okay? So, to prove or to state weak regularity, remember that we consider shifts of the perturbed Brownian motion by predictable processes in some space. Okay, so such a process, if you wish, such a process satisfies an equation of this type. Okay, so this is the initial equation, which will give you this term and this term, but then there is an extra term which comes from here, which gives rise to this additional term. Okay, so V is random here. Okay, it's a predictable process which is bounded. But this equation actually also covers the formulation of the skeleton, because you may consider the case where epsilon is equal to 0, so that means that this term here will disappear, okay? And then you may consider the case where V is deterministic, okay? And then you will have the skeleton. So actually, such a formulation covers both equations, which are important in the sequel. Okay, so as you have seen here, there is in relation with the equation we have considered with Dalang, there is this extra term, right? So what is the meaning we can give to this term? So this is not difficult, because it turns out that, so this is a pathwise integral, okay? Even if this is random, this is a pathwise integral, okay? And then if you assume the same assumptions as for the stochastic integral, so remember that we wanted to define a stochastic integral, something which look like that, and then differential of the noise, okay? So here you have a different integral, which is a pathwise integral, but assume that the same assumptions are satisfied. Then you can, by doing explicit computations, you can see that actually this defines a random variable which takes values in L2. So this is not very difficult, because here you apply Cauchy-Schwarz inequality, and since the norm of W is bounded, so you get rid of that, and what you have at the end is something which is very, very similar to what you encounter when trying to define the Dalang and Müller integral. So it's more or less you face the same problem. So this term is well defined. No problem about that. Okay, and of course, in order to give a precise meaning to the large deviation principle, I have to assure that the equations I am dealing with have a meaning and live in the right spaces. So that means that what I have to do is to extend or resolve with Dalang to these equations, which are more general. Okay. Okay. This is not a big deal. It's just a matter of time and of energy. I mean, so the theorem is exactly the same. Okay. The difficulty is that you have this extra term, so you have to see, you have to go through to the proof. Of course, there are 80 pages, so it's a pretty long, but you have to go to the proof of the initial result by Dalang, and to see that if you add this extra term, well, you work this extra term and you get similar results. Okay. So we can prove also the Hilder continuity. And so the important thing is that these estimates here are now uniform in epsilon and in V. Okay, there are uniform in epsilon and in V, and the procedure is the same as I pointed out before, except that you have to be sure that you have always uniformity in epsilon and in V. Okay, so therefore, the equation and the equation we need, which is this equation, has a solution.
Just a question on the previous slide. Does the constant C depend on n?
Yeah, sure. Yeah. So yeah, I should mention that. Yeah, I mean here this constant will depend on n. Yeah, but n is fixed in all this. Yeah. Okay, so this gives you the fact that the solution to this equation lives actually in the space of Hilder continuous functions too. Right? So now the first ingredient for weak regularity. So now we have to check assumption H1 and assumption H2. So the first one is that the set of skeletons is a compact subset, okay? But this is a Hilbert space, okay? So then it suffices to prove that whenever you have a sequence of HNs in this space, such that they converge to an H in the same space in the weak topology, okay, then you have also this convergence now in the alpha Hilbert topology, okay? So this is what we have to prove to get H1. And to have H2, so it was this stability. So you consider a sequence of elements which are predictable processes, so now they are random, unbounded, okay, which converge in distribution to V, but in the weak topology, and you have to prove this convergence as alpha Hilbert continuous valued functions, okay? So now, in order to prove that, I don't know if Annie has mentioned that, because I left for a while. I'm sorry, just 1 minute. So to prove that, well, also in the literature that Annie mentioned, they use a Skorokhod representation theorem. So that means that by changing the underlying probability space, you may assume that the V epsilon converges to V in the weak topology almost surely. And then it's sufficient to prove that this converges, for example, in LQ, okay, that you have this convergence in LQ. But then it turns out that what you have to prove actually is only that, because to prove H1, I should prove that. But these equations are particular case of the second ones. Okay, this is what I mentioned. So if you take V epsilon to be deterministic and epsilon equal to 0, then you get the equation satisfied by the skeleton. Okay, so it suffices to prove a result like that. So now we are dealing with the Hilbert norm jointly in T and in X. So how to proceed? So one idea we would like to use really all the results that are available, okay, and not to work, for free. So then there is a device that we have discovered, but actually is quite a standard in this joint article with Vlad and Annie, which gives you a way to deal with this convergence. In fact, if you have a pointwise convergence for any Q, and you have nice estimates for the increments, then you have convergence in the Hilbert topology. Okay, so if you fix Q, this is false. Here there is an argument of Garcia-Rodimus-Ramsey, and you have to adjust the Qs. But if you have these properties for any Q, then you have that for any Q. Okay, so the precise statement without where this argument on the change of Q is made precise is given in that article. So here Q is arbitrary. So that means that I have to prove two things, that one and that one, right? So let's give just a feeling of the first one. So the first one, so you have an equation for that, an equation for that, and now you put together terms which are similar. And terms which are similar are that one, so for V, that one, so I put together sigma, and then, well, here I have introduced an extra term, so this gives me that term. So this I should keep carefully, because the hypothesis is that V epsilon converges to V in the weak topology, okay? And then I have the stochastic integral, which goes by itself, because, well, cannot be, it's an extra term. So now, these two terms will replicate that one. When you estimate when you try to find LQ estimates of these two difference using so Hilbert's inequality and so on, so they replicate the first one. Okay, so you can have something like that, well, by more or less standard computation. So this you keep it because at then you will apply a Gromwell's lemma argument. Okay. So then, what about the second one? So for the second one, we are not you don't have the same problems that you encountered because, well, we have a deep knowledge of the properties of the solution. So there are alpha-Hilbert continuous both in time and in space, and we have, nice estimates. So we are able to prove, using all the machinery of the equation, related to the equation, that this process actually takes its values in HT. Okay, and therefore, I mean, by the formulation of the weak convergence, this term will converge to 0 almost surely, and then we can use bounded convergence to conclude. Okay. So here, I mean, the difficulty is to deal with the wave equation itself. So and then for the stochastic term, so this is also quite a standard. We just, there is a square of epsilon in front of, okay, this will go to 0 as far as I prove that this is bounded, okay? And here I use, so the estimates for the LQ norm of this stochastic integral, okay? And by the properties of the solution to the wave equation, the uniform estimates in U and V epsilon and in everything, I have that this is finite, okay? And then just to end up, there is another ingredient, which are the estimates of the increments, okay? So it was the point-wise convergence plus estimates on the increments. But for the estimates of the increments, the work has already been done, okay? Because I have to prove that. But as I have said, V, now V is random, it's a predictable process. But this is a particular case of this equation again, okay? And for the equation, so for the process U epsilon V or V epsilon, we have already proved such an estimate, which this together with this by the Sobolev embedding will give you that estimate. Okay, so the work, well, for the control of the increments is essentially done. Okay, and since it is snowing, I think that it's a nice time to finish. So these are the more so the precise references, and of course I have skipped a lot of references of application of this method to other sort of SPDEs, but for this I think that Annie has mentioned quite a lot. So these are the more basic references on the method. So that one and that one, essentially in infinite dimensional, and so this is our article, and this is the preprint I recommended. So thank you very much for your attention.
Thank you. Are there any questions?
You mentioned at the beginning that you are dealing with a difficult case where three-dimensional, where the fundamental solution of the wave equation is measured on the sphere. How this depends on constant of the coefficient. So if you take instead of a Laplacian second-order symmetric operator with very smooth coefficients, does your result hold in a kind of a natural way, or a work has to be done?
I haven't looked at that problem, but I think that it should not be. I mean, putting the right assumptions, it shouldn't be a problem, because the stochastic integrals.
But we will no longer have this property, but this fundamental solution.
Yeah.
No fundamental.
Yeah. So then, then I don't know. Yeah. You mean you cannot? You can.
Because your situation is that you have a convolution because the
Yes. I use a mile.
There's no convolution.
Yeah. So then you should deal with the weak formulation or something like that.
No, I think you don't know.
Yeah. I mean, I haven't tried, and I am not aware of work like that. But in principle, it could be possible, I suppose. I mean, having this explicit formulation, so this Mile equation, and dealing with you know the precise form of the uniform measure on the sphere was really fundamental to prove that the solution belonged to this fractional Sobolev space, because you know these owns to very specific estimates. So.
Professor Zarczyk.
Yes, I would like to advocate a different method of dealing with such noise. I think this especially homogeneous noise, which was introduced here, the integration can be dealt in many ways. I think there is one way which was formalized finally by Dalang and Müller, but I think, say, starting from '96, we dealt with Szymon and many other people with, say, classical approach. You can treat the homogeneous noise as a Wiener process in the space of distributions, but you can treat it also in a Hilbert subspace of the space of distribution, which is naturally introduced. So I think the integral can be, as you wrote, you know, that the classical integral can be identified with the Dalang Müller, and say, for instance, what Szymon did, he proved existence of wave equation, of stochastic wave equations with such noise in any dimension. I think this say, functional approach has some advantages. But you got here, say, Helder continuity, but we worked in Hilbert space, in L square. Now, let's consider this analytic approach, say, functional analytic approach. I yesterday described a large deviation principle, not for the trajectories, but for fixed time.
Yeah.
I think, as I mentioned, one can apply it to the wave equation with some price. No, but at a fixed.
So then it's a large deviation principle on the space of.
Yes, I think one. So there is a possibility to get probably something weaker, but in a classical way, in a more classical way.
Yeah, thank you very much. Actually, well, I focus on these two types of integrals because these were the stochastic integrals that had an interest in my lecture. But well, I completely agree with you. There are other possibilities, and actually in this article, when the connections within different integrals is considered. The integral you mentioned also is considered. And
so this is 2008 article you mentioned.
Yeah, the 09. So the article, yeah, by Dalang and Kerr. Yeah. So I don't know. I am more familiar with the so to say Walsh approach, but you know, at the end it's more or less the same.
Yes.
So, and then another thing is that I haven't said that concerning this variational method. So, in my opinion, it has a lot of advantages in the sense that this transfer principle by dos priore and so on is quite tricky. But on the other hand, it's really for Gaussian. I mean, for transferring a Gaussian. So this is maybe a drawback because. Well, maybe it can be generalized, but you know, Girsanov plays a very important role there, so I don't know, maybe extra terms or...
Another question?
One question. The starting point of this weak convergence approach is somehow like the solution to your SPDE can be represented as a measurable map of your noise on the path space.
Yeah.
So for SD in finite-dimensional case, I mean, this is somehow no problem for strong solution. But when you come to this infinite-dimensional case, there are different ways to define your solution. Is these things really
Yeah. Well,
automatically comes out?
yeah, there is no problem with the mild solution, and actually this is quite well explained in the article, the VDN article of 2008 I mentioned. Yeah. Because in this article, so they revisited the method, so to say, but then they apply the method to a reaction diffusion equation. Okay. And also, for example, in the talk by Tusheng yesterday, so he applied the same method to a parabolic equation with reflection, and so it was the same problem. So he used but this is not a problem. Okay.
More questions? So I have a question. What about large deviation for invariant measures?
Well, next step.
Do you have a invariant measure?
Probably, definitely.
I have no. Yeah, it's interesting. Yeah. We should definitely move in this direction.
If there are no more questions, so thank you again. Thank you.